All right, so I'll get a full screen here. So this video is going to be a little bit about reflections and taking a little inventory, a little look at what we've looked at for the past month. We haven't had, 31 days of practice. We've had weekends and long weekends and snow day here and there. So somewhere maybe in the 20 to 22 range of days of study. And we got another 20 or 22 days of study before the midterm. So let's take a pause and let's talk a little bit about where we started and where we are. All right, and in my mind, that's a reflection and a little inventory taking. All right, so day one, I said we got the rule of 4 at play. And for me, that means we look at something 4 days in a row. We don't have to look at it for long, a minute here, a minute there. But if we do that for 4 days in a row, a lot of times what you're looking at starts to have some meaning. And so that's the approach we've taken with a lot of different problems, which means that maybe we can make a lot of gains in a short period of time. All right, because when we started, writing the equation on a line was not easy, and most people couldn't do it. And now, seeing everybody do it, and pretty quickly and easily. And we're trying to do that with every problem. So remember the rule of 4. All right, we set goals. One of them was learning how to learn. And I just talked about it 10 seconds ago. Looking for patterns, okay? And maybe even learning how to think mathematically. Now that sounds really nice. That's why I included it. Am I sure I know what that means? No. But it sounds good. All right, so that's where we were. And then on day one, we talked about the history of mathematics, and I asked the question, well, what was the first mathematical thing probably that occurred? And I don't know. I wasn't there, although I had friends back then. Right? But I did this. I went, mark on the cave wall, notch in a tree, something, a symbol that represents a quantity. I think that's where it started, right? And then I think addition and subtraction came along, and multiplication and division, and powers, and roots, and exponentiation, and logging, and so on and so forth, integration, differentiation, so on and so forth, right? And how do we read math? Not necessarily left to right. No, that's one thing that makes the language, which I said, math is a language. I don't know if you remember, I wrote this sentence. Write this symbolically. Can I capture all of it? Yeah, I'll have to remember to move that screen in a minute. The exponent you put on top of a 5 to get the quantity 25 is a 2. And for anyone who's never had that expression explained to them before, almost always says 5 squared equals 25. Almost always. But that's not what I wrote. And maybe you now know what I wrote. Maybe it has more meaning for you. The exponent you put on top of a 5. Well, that's what log base 5 is all about. Log is the value of the exponent. That's what that means. The value. I should have put value in here. I think I wrote value day one. The value of the exponent. The value of the exponent you put on top of 5 to get a 25 is a 2. And we're trying to learn to rewrite 25 in the base given. And so the log is that exponential value. Okay, so that's something we did day one. We also talked about, please pardon my dear Aunt Sally. And, she got part of it right, but I don't ever remember talking about exponents and logs or sine and cosine and inverse sine and inverse cosine. I don't remember that being in the mnemonic. So how is math done? Well, it's evolved historically. It's evolved. Maybe it's been discovered. More discoveries happening. I think there's a controversy there, whether it's discovered and it's always been there or whether it's evolving. I don't know. It's above my pay grade. All I know is we basically do parentheses first. Sally got that. Good job, Aunt Sally. You do parentheses first, but then you basically go hardest operation to easiest. That's basically what you do. And then you might even have to repeat hardest to easiest if there's an argument that's more complicated than parentheses x. And that's what lesson 12 was about, which I'm going to explore in a moment. Okay, lesson 12 is going to get explored in a moment. All right, so, and we also talked about multiplication. And I said, I think I asked a student in class, can you do this for me, please? 17.45 times, how about 9.31? Quick. No, couldn't do it. Oh, somebody's calling me. I'm gonna let it go. Maybe not. Yeah, I'm gonna let it go. Sorry, Bob. Talk to you later. All right, so back to this. Multiplication. 17.45 times 9.31. I don't know how to multiply that. Well, what would have been the easiest multiplication? 0. And you know what? The student got that right very quickly in under 2 seconds. And I said, what's the next number that's easiest to multiply by? 17.45. And I think the class said 1. I'm wondering what the next easiest one is. Well, you can pause the video for a minute. And then the next one after that, I'll give you my rendition. Okay, but you pause the video and think. I think it's actually the number 10. I think it's our number system number. Right? It's easy to work with. In fact, if you had 12 times 18, and you wanted to do that in your head, well, you could write 18 as 10 times 10 plus 2, and 8 times 10 plus 2. Right? There's 10 and 8, 18 times 10 plus 2. And I think it's probably, oops, I botched this one, didn't I? Not really, because I got a multiplication by 10. I see 100, I see 20, I see 80, I see 60. I think you can do that in your head. All right. What's the next easiest number after 10? I think it's 2. Yeah, rule, you know, bankers have a rule called the rule of 7, which means that they're interested in compound interest and they want to know how long it takes to double something. Well, doubling something in E notation, because that's what they work with, doubling something is 0.7x. There's the rule of 7. And that allows you to quickly and easily figure out how long it takes you to double your money if you got a 4% interest rate. Turns out that answer, and we haven't done it yet, but planting a seed, ln of 2 divided by 0.04, tells you how long it takes to double at a 4% compound interest at a 4% interest rate. How long does it take to triple? ln of 3. And then you go ahead and you say 1.1 divided by 0.04. And I hope you understand the importance of multiplying by 10, which makes 110 divided by 4, which is 20, what, 7.5 years to triple your money? Right? So all these things are going to mesh into other things. All right. And yesterday we did lesson set 12, which was broken up into 2 major parts: solving equations and seeing the pattern that comes from a certain type of equation, which I'm going to go over again now. I'm a big fan of repetition. In fact, I'm such a fan of repetition. The other day I did this, just started playing with the dimensions, and I put x to the 4th, and on the other side I put x to the 3rd with an x, and it was this picture, and I was looking at when do these things equal? Right? And it's been 4 days since I did that problem, and I've been thinking about it a little bit, minute each day. And all of a sudden I said, well, you know, if this was in meters, meters times meters times meters times meters, I don't know what the drawing is, but, you know, 1 meter measures distance, 2 measures area, 3 measures what? I'm drawing the cubic, right? So what's 4? I don't know how to draw it, but if I have something to the 4th power over here in terms of units, then I have to have the same thing over here. I have to have exactly the same thing. So here's x, here's x, here's x, here's x. Well, I can see x squared. That's this one times that one. But what's the length? Well, the length has to come from this. And it's got to be meters to the 4th. I got to get meters to the 4th, which means it's got to be the square root of 3 and the square root of 3. So I get something that's 4-dimensional, or negative root 3, right? I could have made everything root 3, root 3, root 3, root 3, root 3. Then this has to be root 3, root 3, because they all have to be the same. Or negative, right? Negatives work too. And there's one other that works, and they don't have to be the same. And what is the other one that works? 0 times 0. This could have been 0 times 0 as well. And it doesn't matter about these, because when you multiply something times 0, you get 0. And when you multiply something times 0, you get 0. I'm rushing now. But I've talked about this already several times, so I should be able to rush and you should be able to follow. That's the hope. Okay, so does it explain? Take out what's common. If you do, and you make this into a zero, and you do take out what's common, which makes a zero equals zero, when x equals zero, then you're left with x squared minus 3 equals 0, and hopefully you can see where plus and minus root 3 come from. Okay, so it takes repetition though, and it takes time for your brain. So what are we going to do now that we have it in front of us? We're going to work with it until May 15th. And then I grade you. Okay, so what was lesson 12 hoping to accomplish? Well, one thing is we figured out that guesstimating this, thank you, Imogen. Imogen gave us the word guesstimate in class yesterday. I'm going to use it. I like it. We're going to guesstimate pictorially, right? There's a picture, and people had trouble with the picture still. So we went to point by point analysis, put a 1 in, minus 2 squared, 4 times 2, 8 plus 4, 12. That's not 5. Put a 2 in, 1 times 2 plus 4 is 6. That's not 5. Put a 3 in, 0 gets me 4. That's why it's so important, and that's a minimum. Everything else is bigger. 4 gets me 6, so on and so forth. So I got some answer between 2 and 3, because 5 sits in between 6 and 4. And how do we find it? Okay, well, we get a picture, we approximate. Sure looks like it's pretty close to 4. How far is it? How far is 5 from 4? Appears to be 1 unit. And what's the first operation that we do? We subtract 4 on the other side. Why? Because the order of operations here, subtract 3, right? So we got to put a number in for x. Pick a number. First thing you're going to do to that number is subtract 3. You're then going to square it. That's what I did to get these values. I squared it. Then I multiplied it. And then I added 4. And when we're solving, we have to use inverse operations. I just did addition of 4 becomes subtraction of 4 on the other side. And I don't want to see this on anybody's paper. I really don't want to see that. We're trying to learn math. For God's sakes, everybody knows how to subtract 4 from 5. So do it. Well, okay, so that's now gone. What's the next thing we do? Well, in the evaluation process, to get all these numbers, I squared next. And that's where math isn't left or right. I'm in the middle of a problem, and I'm, moving around a little bit in terms of language. But I'm dividing by 2. So that gets me a half. That takes care of that. It's kind of like getting lost in the woods. You're at a rock in the woods. How do you get back to where you started from? You retrace your steps. And if you moved east, moving east is adding 4, then you got to move west to get back to that location. So added 4 becomes subtraction of 4, multiplication becomes division, squaring becomes square rooting. And I don't know if you know that, but the square root of 1 over 2 is a very important number in trigonometry. Right? The square root of a half. Well, I think we got to bring Pythagoras in here. That's a 45-degree triangle. And that's the square root of a half. And so what's the area there? A half. What's the area over here? A half. And if this is a right triangle, 1/2 plus 1/2 gets us an area of 1. Yeah. Yeah, a half plus a half. Yeah. So what is the square root of a half in trig? Well, if you do the rationalization, another way of naming that is plus or minus root 2 over 2. And we're going to be working with that extensively soon, very soon. Okay, so that takes care of squaring. Subtraction of 3 becomes what? Addition of 3. Now, could you have gotten that answer from here immediately? I hope so. The only x value I have is 3. And I know one of my answers is to get an x-axis superimposed here. It doesn't matter. It's just horizontal change. I'm going from 3 to someplace over here. Well, I hope you say 3 plus. And I'm also getting one over here that will get me that y value of 5. I hope you say minus. Okay, and there's what you needed. Square root of 1 is 1 over root 2, right? And there's your root 2, just to show you the rationalization. And so your answer off a calculator would probably be root 2 over 2. And you can substitute it back in and prove it to yourself that it works. Unless Yasser's catching a mistake of mine. And I hope you keep your eyes open, Yasser, because I'm not stopping. All right. And so there's an easy method here for finding roots. If something's in graphing form, I'll give you something in graphing form. And before I give it to you in graphing form, let me just give you a quadratic. Let's say this is 3, 7. And this is, oh no, I want to give you an A term. Let's say A term is 5. Very narrow parabola going up fast. And we want to know when it hits 0, the roots. Okay, so you pause the video. I'll just write the answer based on something I randomly picked. Again, we're measuring from 3. How do I get from 7 to 0? I got to go down 7 units. What's my multiplier? A 5, and I'm taking a square root. And I hope you see why. I'm going to take the negative out and say I got imaginary points of intersection. Right? I'm imagining it really turning down in the other direction if you want to actually see the numbers work. And so all of this is stuff that we're talking about. Now back to lesson set 12 and the equations. And the best question someone asked, and it happened to be Imogen again, we'll get to it in 5 minutes. But let's solve a variety of equations that are similar, and let's see if we can see the patterns. Okay, so very similar problem here. What's the first thing you're going to do? I hope you subtract 1. I hope you divide by 2. And now where are we at? We're at the ln of x minus 3 equals a half. We're at the major operation. We're at big F of x. Big F of, well, it's not big. I'm thinking calculus here if I want to capitalize the F. We're at the major operation, this function. So how do we get to x minus 3? We need the inverse of the ln. We got to do the inverse operation. The same we did the inverse of squaring, we got to do square rooting for a problem like this. And the inverse of ln we're trying to learn is e to the 1/2. Now, I don't know what e to the 1/2 is. It's very easy to confuse it with the ln of a half, which is approximately negative 0.7. So it's easy to be dyslexic here. So be careful. E to the 1/2 is really approximately the square root of 2.71. Remember, something to the 1/2 means square root. So what's my final answer? The square root of e plus 3, which is around 5.71, I believe. It's around there, right? And then we were practicing the graphing to see if that answer made sense. So let's remember what our answer is, around 5.71. But we were doing the graphs first. And I'm hoping that you can see that graphing, you know, if we can make this thing 0, whoopee, we get C. Because anything times 0 goes. And if we can make this 1, we get n minus c plus m. I didn't write that. I did multiplication here. I'm evaluating now, not looking at the solving. I wrote the solving process down here. Okay, but I'm graphing now. So if I'm graphing, I want f of x to equal 0 for good reason, geometric reasons galore. There's geometric reasons galore with that. And I also want to make this f of x equal 1. Because 1 times m is m plus c. Right? And I'm going to do that here. Well, bad choice on my part because I am actually going to look at the ln of 3. Okay, so this is actually a little bit of a special case. All right, so let me erase this. I see x minus 3. I know that's my asymptote. We'll examine that more in class. Positive 3, excuse me. I know that I have the inverse of growth. It looks like that. So I'm going to pick a 4. If I pick a 4, I'm going to get a 4. Why? Well, we're trying to learn b to the what? B to the what equals 0. Equals 1, excuse me. B to the what equals 1 and b to the what equals 0. Nothing equals 0. So let me get straight what I want to say. Let me just do the problem. So I picked a 4 because I get this. That is 0. And 2 times 0 plus 4 gets me the 4. Now I want to pick the number 6 and see if, given what we've done on previous lesson sets, you can guess why. And the reason is whatever that distance is, I want it to be about 3 times. I want a 3-to-1 ratio in these problems. So if I put 6 in there, I get the ln of 3. The ln of 3 is approximately 1.1. I'm doubling that, and I'm adding 4. So 6.2. 6.2 roughly gets me 6 units of change. Okay. Then where am I at? I'm at 5.71. Where's 5.71? Probably around here. Probably around there. Does it look like that might be 2 units over at 5? I think so. I think so. I think it's believable that, more than 2. 5.71, I think, is what we found, right? As an approximation. It looks good to me. 6.2 to get 5. 5 is probably here, a little further along, but it's a guesstimate, right? Imogen's word I like, guesstimate. And this process requires an inverse operation for some operations that are new to you. Okay, and we're going to look at those right now. And we're going to figure out how to get past step 3 in solving equations like this so you can do it easily. So, how do I get x alone? Well, I hope you say plus or minus the square root of y. Now, what is y? Y is some kind of altitude. We have different altitudes on the y-axis. And if I'm over here, let's say I'm at a height of 6. Oh, I've got a 5 here. Let's say I'm at a height of 5. So how do you solve this? You say x equals plus or minus the square root of 5 when you get to that point in a problem. Okay, and we just did one a minute ago. So let's do one more quickly and see if you can come up with the answers. Let's say minus 2 times x plus 5 squared minus 7 equals negative 50. Okay, can you get an answer here quickly? Well, first thing you would do is, first off, that's this, right? And I've got a negative 5 gets me negative 7. That's why I like the left to right. And negative 50 is way down here somewhere. So how far do you have to go from there to get to there? Looks like you got to go down 43 units. Well, what are you dividing by? Negative 2. So we have real roots with a what? Plus minus square root. And what am I measuring from? Negative 5. I want you to see that. I know some folks out in the internet land are seeing that. I want everybody in this classroom to see that. All right, so what do we have next? Let's do it here. I had a little bit of a sketch. What's your first step? I got to do it here. Add 7. I'm at negative 43. We just talked about that. What do you do next? You divide by 2. That gets us real roots because a negative divided by a negative is a positive. That takes care of that. What takes care of squaring? Plus minus rooting 43 halves. Do you have a feeling for 43 halves? It's near the square root of 21, which is between 4 and 5. Start to get a little feeling for what you're looking at. You want that to happen. And we're measuring from negative 5. Hopefully that's what I said a second ago. Then we did a cubic, a perfect cube. These get a little tricky. But why is 0 so important? Well, a cubic looks like this. Right? In cubics, the volume of cube, the rate of change is attached to the square area of the cube. We'll develop that thought in the second half of the term. Well, pretty hard to change much if you don't have any volume. If there's no volume, then there's no change, and that's why it's flat there. All right, I think I talk about this on the other board more later. But what's the inverse of cube rooting? What's the inverse of cubing? Cube rooting. So what's the cube root of 8? Well, here's a height of 8. How's that differ from the quadratic? I'm not putting a plus minus in front of this. It looks like I picked that one down here. All right, there's only one intersection. So we don't put a plus minus in front of that. Next, square root of x. Why is 0 so important for the square root of x? Well, here's a square root right there. It's got some size to it. What if I had a smaller square? Or a smaller square? Or a smaller square? I hope you see that the smallest square I can get is 0, even though I can't draw it. Something times something gets me something here. That's true. So when does something equal 0 is very important to our graphing. All right, if I'm going to graph 2 times the square root of x minus 3 plus 4 equals 18, I think that's what was on the test. Then what am I going to do? I'm going to show it by making 2 times the square root of 0 plus 4 on the left. Well, that means positive 3 gets me 4. Let's call that 3, 4. Just estimate, real guesstimate. Right? And what does happen? Well, if I make this 25, then I've got another place on the curve. I don't really want the XY axis. I'll just let it stay by itself here. So I'm going to pick 28. Because if I pick 28, I get this calculation, and I don't need a calculator for that. I get 14. So let's just say that that is now 14 units high. And it took 28 units, right? So that's 10 units of change. I need another 4 units of change, but this thing is going up very slowly because it's the inverse of the squaring process, which goes up very quickly once you get past x equals 1. Faster and faster, there's acceleration, deceleration in the inverse. All right, so what's the answer? Well, why can't I just go and work in the vertical direction and say, subtract 4, divide by 2, square, and add 3. Is it believable that somewhere way out here, 52 is going to get me a height of 18? I think so. And it's a similar thought process. You just got to get to that third step and know the inverse operations, which is what Imogen asked. Right here, what's the inverse operation of this? Great question, because that is exactly what the lesson set was for, was to make that connection. You need to know all the inverse operations that we are learning how to evaluate. All the functions, e to the x, what's the inverse? ln of x. Log, well, we'll get to it. They're on the board. So what is it? It's plus or minus y. Let's take a look at, that's the shortcut. Let's say we have x minus 3 equals 7. All right, so what does x minus 3? I'm getting rid of that operation. It's got to be plus or minus 7. It's got to be. Right? I got to get a number that comes from this. And then the next step is 3 plus or minus 7. Well, let's say 10. Does 10 work? Hope you see that works. Does minus 4 work? Minus 4, minus 3. Take the absolute value. Yeah, they work. So when you're solving absolute value, the quickest way is to subtract 9, divide by 3, and now I'm at the absolute value. I got to do plus minus 6. Now, this is a little more complicated. I decided to make it a little more complicated because we're kind of in a grouping symbol here. So I got to deal with this now, right? So why don't I start with the positive 6 over here and the negative 6 over here? A little bit more space would be nice. So I'm going to run into a little bit of difficulty. So what am I going to do with minus 1? I'm going to add 1. What am I going to do with the 4? I'm going to divide by 4. That number should work. What am I going to do with positive 6? We don't need the plus sign there. I'm going to add 1. What am I going to do with the 4? I'm going to divide by 4, 7 fourths. What's 7 fourths minus 5 fourths? 2 fourths. What's 2 fourths cut in half? 1 fourth. What's the critical number in this problem? 1 fourth. What does 1 fourth do there? It makes the absolute value a 0. Absolute value measures distance. What's the shortest distance you can travel? Stay home. Don't. That's the smallest distance. And so when I look at this, I know that 1 fourth gets me my minimum value of 9. And I at least know the vertex of that. Yeah, I know a lot more, but we're just diving into this. Could talk more about that and will later in the term, because we're going to be doing a lot of things with absolute value. So 2 to the x equals y. If you're going to solve an equation, an exponential equation, then you need the inverse of that. Some of you now know the inverse of that. Some of you don't. That's the inverse. So if we wanted to rewrite this, the 2 is equal to log base 5 of 25. And I hope that means more to you now than it did a month ago. We're going to keep talking about it. And we just did a repetition on a theme. Boy, I really wound up here today. All right, e to the x equals y. What's the inverse? ln of y. So let's solve a complicated e to the x problem. And let's just get an exact answer. 4 e to the 2x minus 3 over 7 plus 9 equals 100. Step 1, you pause the video, see if you do what I'm about to do. 91 over 4. ln of 91 over 4 times 7. 7 ln of 91 over 4. Add 3. I'll do it here. And then divide everything by 2. Okay, that's what the answer is. Exact answer. Written very poorly, like third grade handwriting. All right, so what's the inverse of log base 3? Log base 3 of x. X equals 3 to the y. That's the inverse. What's the inverse of ln of x equals y? X equals e to the y. And the only log you haven't seen so far that I haven't given you in class is this one. All right, this is called a common log. Okay, why? Because it's base 10. If we don't write, if you see log without a base, it's understood to be base 10. That's our number system, right? And Napier did his whole log tables, I believe, in base 10. I think I'm right, right? And once he did, then people started studying the distances to the stars. Okay, Enlightenment period. Good to know. Okay, let's see. I got to get Rene Descartes to make a U-turn here. Okay, got to get past Park Place. Got to get to Boardwalk. I just dated myself. There we go. So we're just starting to talk about sinusoids. Okay, and you haven't been introduced to this unit circle yet. Probably next week. We'll probably dive into that. But I hope you can see why it might be the following. Okay, we have this thing called evaluating a function, and this is the inverse of the function. And the function we're looking at right now is that command. Very important that I keep mentioning at this stage of the game. What does X stand for? You have to know what it stands for in order to have success with trigonometry. Okay? And it stands for an angle. So with this language system, this has got to be angles. And angles can be written in degrees, which you're familiar with, or radians. And that's what we're going to be using because that models things. It models things better than degrees do. So we can study things out there in the real world. And we started doing that with these functions, right? Those are on your, and we haven't even done the unit circle, and yet we can still write these graphs based on our knowledge of how to write the equation of a line in just a few radian measurements. And we've been doing that in the previous lesson sets. All right, so here, I wanted to make sure I talked about compound interest a little bit. Rule of 7, multiplication, I guess I've already done that, did it early on. And so now, where do we go from there? Well, I'm hoping that I can at least occasionally, for those students who are really moving along quickly, talk about some of these table values and what they mean. That's where I'm hoping we can go in the second half. I think I've been talking way too long at this stage, but why are zeros so important? Well, geometrically, they're important. I have a function that's going down and going up, and the pattern starts there at 0. Why? 0 squared is a minimum. You put any other real number in here, and you're not getting a minimum anymore. So why do we have minus b over 3a, over 2a, excuse me, in the quadratic? So we can find a value like minus b over 2a equals 5. What do we do with the 5? We make it a minimum if it's the vertex value, because now when I drop a 5 in, I get 0 squared, which is a minimum. And we're doing the same thing with cubics. All right, why is minus b over 3a so important? It gives you the point of inflection. If you'll notice, my volumes are negative, but going up. And at 0, there's no surface area, right? And these are actually surface areas. We can get surface areas out of those tables, but I think I should stop there. You know, I'm really putting a lot of thoughts in people's heads. All right, but we're going to develop those themes later in the term. All right, and anybody that can go up 3 or 4 points each test is doing fine in my class. I know you're used to percentage scores. You know, I'm making these videos for my classes. You're used to percentage scores. Don't think that way. All right, pick up a few more things to put in your pocket, a few more things to put in your pocket, and you'll learn something about integration. A lot of small changes over a long period of time add up to a big change in hopefully your understanding of algebraic foundation. All right, there's my lecture. And now I'm going to, later this afternoon, take a break, let my brain take a break, and then I'm going to do a 65 lesson set that we'll spend 2 days on. And then we'll take a test and see if we can do a little better than the last one. All right, toodaloo. Can't find my cursor. There it is. All right, have a good day. Still snowing here.